This is section 5.4 of AP Calculus, particle motion problems. This, I think you'll find, is pretty awesome. Particle motion problems deal with particles that are moving along the x or y axis. Thus, we are speaking of horizontal or vertical movement. The position, velocity, and acceleration of a particle's motion are defined by functions. But the particle does not, all caps, move along the path of the graph. It moves along an axis. Most of the time we speak of movement along the x-axis. In Units 6 and 7, particle motion is revisited. At this time we will deal more with vertical motion. I'm sorry, at that time, not at this time. That's future, not present. For the time, that's right now, we will focus on vertical motion of particles. In this lesson, we develop the ideas of velocity and acceleration in terms of position. Position is the same as displacement. Not the same as distance traveled. Displacement and position, same. Distance traveled, not same. We will speak of two types of velocities and accelerations. Let's find the average and instantaneous velocities in the boxes below. Hopefully looks familiar, even though we've never actually talked about average velocity. Average velocity on a closed interval is the position at a given time minus the position at a different time divided by the difference of the two times, where P of t is the position of the particle. Instantaneous velocity at a specific time c, you take the derivative of the position function and evaluate it at c. That also should look familiar from a different context. This next problem requires a calculator. A particle's position is given by the function P of t equals e to the t times sine of t, where P of t is measured in centimeters, super important, and t is measured in seconds, super important. Answer the following question. What is the average velocity on the interval from t equals 1 to t equals 3 seconds? Include appropriate units of measure. Just as an example. Big picture. You drive from here to Canton, here being wherever here is for you. Let's say that it takes you 1 hour to get there. And let's say the distance from here to Canton is 60 miles. What was your average velocity? Well, your average velocity was 60 miles per hour. Does that mean you were traveling at 60 miles per hour every instant? Well, no, that's preposterous. You can't go from 0 to 60 in no time, and you can't stop from 60 to 0 in no time. Average velocity. Here's what we do. We use the formula average velocity is equal to the position at time 1 minus position at time 3 divided by 1 minus 3. If we plug 1 into the function, we're going to get e to the first times sine of 1 minus e to the third times sine of 3. 1 minus 3 is negative 2. Put that in your calculator. You're going to get 0.274. How do we label this? It says centimeters and seconds, so it's centimeters per second. Part 2. What is the instantaneous velocity? Instantaneous velocity is instantaneous rate of change, that's derivative, of the particle when t is 1.5. Indicate appropriate units of measure. Even though we're allowed to use a calculator for this, we're not just going to throw this whole thing in our calculator and get an answer. We're going to show some work and use a calculator when the calculation gets tough. To find the derivative, it is the product rule. Take the derivative of the first, that's e to the t, the derivative of that is itself, times the second, sine of t, plus the first times the derivative of the second. The derivative of sine of t is cosine of t. That's the instantaneous rate of change. That is the velocity, which I should label it as such. Let me be a little more specific here. My apologies. This is v of t. This is v of 1.5. This is v of 1.5. Anyhow, once you find the instantaneous rate of change, the velocity, plug 1.5 in, here, 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 and here, throw it into your handy dandy, and you should get 4.787 centimeters per second, assuming I used the calculator correctly. Before we continue, a connection needs to be made, and hopefully you've already made this connection as we just talked about this. When given a function f of x, how did we find the slope of a secant line on the interval from a to b? In terms of particle motion, to what does the slope of the secant line correspond? What corresponds to the average rate of change? See, it's the same function. We just use p's instead of f's. Average velocity on a closed interval, same as slope of a secant line, given the endpoints of it. Average rate of change. Continuing. Average and instantaneous velocity. The velocity describes how the particle's movement is changing with respect to time. That's what velocity is doing. Acceleration is describing how the velocity is changing relative to time. Average and instantaneous acceleration. Average acceleration. You take the velocity at a given time minus the velocity at a different time divided by the difference of those two times. This is on a closed interval. Keep in mind that the velocity is the derivative of the particle's position. In other words, this is the second derivative of the position. Instantaneous acceleration is the derivative of velocity at a given time, or the second derivative of the position function at a given time. Position displacement, same thing. I'm going to keep saying that. Check out an example. A particle's position is given by the function, same function we had before, where p of t is measured in centimeters, super important, and t is measured in seconds, super important. Answer the following questions. What's the average acceleration? So when you think average, it's just the slope formula you've been using since you were a little gangsta in middle school. What is the average acceleration on the interval from 1 to 3 seconds? Indicate appropriate units of measure. Well, to do this, to find the average acceleration, we have to know the velocity function, which is found by taking the derivative of the position function, which we found on the previous page. So to find the average acceleration on the closed interval from 1 to 3, we take the velocity at time 1 minus velocity at 3 seconds and divide that by 1 minus 3 seconds. Put those into the function above, you will get these numbers. 1 minus 3 is -2. Put it in your calculator. You will get the following. Let me give this to you in sentence answer. The average acceleration of this particle from 1 to 3 seconds is -10 and 403 thousandths of a centimeter per second every second. Next question. What is the instantaneous acceleration of the particle at time equals 1.5? Well, to find the acceleration, you take the derivative of velocity, which is the second derivative of position. And you will find that if we take the derivative of this here, we got to use the product rule. We got to use the product rule again. Derivative of the first times the second plus the first times the derivative of the second. So that is all the derivative of e to the t times sine of t. Plus, this is the derivative of e to the t cosine of t. Derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is negative sine. So that is a mouthful. Awkward pause. If you combine like terms, we'll check this out. These are like terms, opposite signs cancel. These are like terms, same sign, so we now have two of those. To figure out the instantaneous acceleration at 1.5, we put 1.5 into the acceleration formula, throw it into your handy dandy, and you get the acceleration, the instantaneous acceleration at 1.5 seconds is 634 thousandths of a centimeter per second every second. Moving on. In summary, let's correlate the concepts of position, velocity, acceleration, what we already know about the first and second derivative. F of x corresponds to position, f prime of x corresponds to velocity, f double prime corresponds to acceleration. Let's summarize these relationships between position, velocity, and acceleration. Big picture stuff here. If a function is f, particle motion, then f prime, I'll tell you what, we don't usually use f for particle motion. Usually we use an s, quite frankly. Say the position is s of t, let's say the velocity is s prime of t. If s is 0, then the particle isn't moving, or it might be turning around. Interesting. If s prime, if the velocity is bigger than 0, then that means that the particle, its position is increasing, which means it's moving farther away from where it started. If the velocity is negative, that means the position of the particle is decreasing. That means it's moving towards where it started. Say that again. If velocity is positive, it's moving away from its beginning. If velocity is negative, it's moving back towards the beginning. If the velocity changes from positive to negative, that means that your particle is changing direction. It's moving from going, uh-oh, I wrote that down wrong. If it's going from positive to negative, it's moving from going away to going towards its target. Target, let me rephrase that. Let me give you a visual. Let's say that something starts here and it's going in this direction. So this is where it starts. If it's changing from positive to negative, then that means that it changed direction and it's going back to where it started. If it's changing from negative to positive, then it was going to where it started and it's changing direction and then going away from it. Velocity, v, which is the derivative of the position function. Acceleration, a, which is the derivative of velocity, which is the second derivative of the position function. If the acceleration is 0, or undefined, that means the velocity is constant. It could also mean that there's a potential change in velocity. If the acceleration is positive, it means the velocity is increasing. So if you're going 55 miles per hour and your acceleration is positive, then that means after that you're going to be going faster than 55 miles per hour. If your acceleration is negative, your velocity is decreasing, you're slowing down. If the acceleration changes from positive to negative, then your velocity is changing from increasing to decreasing. If your acceleration changes from negative to positive, your velocity is changing from decreasing to increasing. 2 more pages. Yay. The graph below represents the position, s, of t of a particle which is moving along the x-axis. Question 1. At what point is the velocity equal to 0? Well, it's equal to 0 I almost said hero, and then I was thinking gyro, and then I was thinking gyro, and it came out weird. The velocity is 0 when the original function has relative max and mins. Another way to say it, the velocity is 0 when the slope of the tangent line is 0. So the velocity of t is 0 at points B and D because S of t has relative mins or maxes. You could have also said because the slope of the tangent line is 0. At what point does the acceleration have is equal to 0? Well, that's going to happen at an inflection point. A of t equals 0 at point C because S of t has an inflection point. On what intervals is the particle's velocity positive? So in other words, when are the tangent lines have a positive slope? From here to here. Now if you don't pay attention to this, you might think, and this is what I did initially, I said the velocity was bigger than 0 from negative infinity to b, because this arrow is going in this way forever. And I'm going to explain why that's wrong in a second. And then it's positive again from d to infinity, non-inclusive because S of t is increasing. Let's examine for a moment why it's not negative infinity. Algebraically, it should be negative infinity. Logically, it shouldn't. T is measured in time. Time is 0 at the beginning, and we are measuring as time progresses in its natural manner, which is not through time travel. You're starting at time 0, and then you're moving. So in most cases, there could be some exceptions, but in most cases, our domain for this is going to go from 0 to infinity. I shouldn't say infinity. It's going to start at 0 and go to a number or infinity. Would probably include the number. Anyhow, that's why that's not negative infinity to b. Next question. On what interval is the particle's velocity negative? That's when the slope of the tangent line would be negative. That's from b to d. That's because S of t is decreasing. On what interval is the particle's acceleration positive? Well, let's look at concavity. It's positive when the graph is concave up. So the acceleration is greater than 0 from c to infinity, not inclusive, because S of t is concave up. On what interval is the acceleration negative? Well, that's when it's concave down. That's from 0 to c. Once again, 0, because we're starting at time 0. We're measuring how something's changing as time progresses. Ready? Here's some important facts. The 5 commandments. Well, these aren't facts. These are commandments. First of all, let's assume the particle's moving along the x-axis. Commandment 1. If velocity is positive, let's use a comma, then particle is moving right. Let's put a comma and a then, otherwise it looks a little awkward. Awkward. If velocity is negative, the particle is moving left. If speed is increasing when the velocity, if speed is increasing, then the velocity and acceleration have the same sign. Let's do this. Let's make this better. Speed is increasing if and only if, so we can say this forwards or backwards. The velocity and acceleration have the same sign. Speed is decreasing if and only if the velocity and acceleration have different signs. Last commandment, if the velocity is 0, but the acceleration is not 0, the particle is momentarily stopped and changing directions. I'll be honest with you, at this point, I don't really follow this part. Here's what I know for sure. If the velocity is 0, then this particle is momentarily stopped. and it may be changing directions. But this is saying if the acceleration is 0 and the acceleration isn't, then it's also changing directions. I haven't wrapped my brain around why that's true at this point, but this is a commandment that I read, so I'm just going to believe it. Blind faith. You know who else says blind faith? Helen Keller. Suppose the velocity of a particle is given by the function, as given, where t is measured in minutes and v is measured in inches per minute. Answer the following questions. Find the value of v of 3. Well, that's easy. You put 3 into the function, which I've done here. Simplify it, we get 245. Label it inches per minute. Find v prime. We got to find the derivative. To find this derivative, we have to use product and chain rule. Derivative of the first times the second plus the first times the derivative of the second. And that second, we're using a chain for this. If you put 3 in for that, we are going to get 119 inches per minute, not squared, just per minute. And then the question is, no, I'm sorry, that is per minute squared. Because this is velocity squared, which means this is the same thing as acceleration. Based on these values, describe the speed of the particle. Now they both have the same sign. Speed is increasing if velocity and acceleration have the same sign. That's commandment number 3. At 3 minutes, t equals 3, the particle is speeding up because the velocity is bigger than 0 and the and the acceleration, which is the velocity derivative, is also bigger than 0. Or we could have said instead of this, because velocity at 3 and acceleration at 3 have the same sign, S-I-G-N. Part B. On what intervals is the particle moving to the left or right? It's asking when is the velocity negative or positive. How do we find when things are negative and positive? We make a first derivative sign diagram. Now keep in mind that the velocity is the first derivative. So we're making a velocity sign diagram. I took the velocity and I factored it and set each factor equal to 0, and I got that the velocity is 0 when the time's -2 and -4. And those numbers don't mean anything to us because that's backwards in time. That's 2 minutes before we started and 4 minutes before we started moving. Doesn't make any sense. So when I made the sign diagram, I started out with 0 and I went to the right forever. There are no v-intercepts, scratch that, no t-intercepts for this that are positive. If I put a test point like 1 into this and this, I'm going to get a positive times a positive, which means the velocity is always positive. If it's always positive, it means it's always going to the right and never going to the left. For all values of t greater than or equal to 0, the velocity is bigger than 0. Therefore, the particle is always moving right. That concludes the notes that we're doing today. Sorry that took so long. Longer for you because you had to pause and write things down. I acknowledge that. Your assignment, should you choose to accept it, and I hope you choose to accept it because I'll break your legs if you don't, is to do 1 through 5 on the homework. Do numbers 1, 2, 3, 4, and 5. Thank you very much.